As promised, we're now back from the break again. Anyway, now we're going to talk about circuit and device representations, circuit design properties, and some of these may be behavioral, structural, or physical. So in general, integrated circuit design is moving further away from the physical layer as technology evolves. A higher level design for basically circuit capture. So it's a lot of reliance on very sophisticated CAD tools to handle much of the error-prone low-level tasks. The lowest level is the physical level, and it also tends to be more easily automated. So programmers don't write a ton of assembly language code, but use high-level languages and their associated compilers. Well, the same thing happens in the hardware environment. You tend not to do a lot of low-level design. You try to code at higher level languages and use a number of compilers and synthesizers. Anyway, a behavioral representation would basically be what the function is or does. And in this case, it's just an example of a logic function. So f is a function of a, b, c, and d. And it's just the logic representation that you're familiar with, or the Boolean algebra. The higher level representations of may also be behavioral descriptions, such as an arithmetic function. So the sum is equal to a and b. Or a behavioral representation of a flip-flop. In that case, it's a small piece of code. If load is equal to 1, then Q equals to D. A structural representation basically specifies the connections between the components to implement certain functions, i.e. the structures and the wires themselves. So here's an example of a structural representation. It is simply the structure, not the function. It defines a part to be an inverter. It has an in and it has an out, and it has an NFET with out, in, and VSS connected as drain, gate, source. That would have been pre-decided by whatever tool is reading that net list, and then a PFET, which has drain, gate, and source also labeled from the out, in, and VDD, and then an end of that part. So it is how it is connected together, and that's what's also known as a net list. To continue with the structural representation for the NFET and the 1PFET, the NFET connections were the drain, gate, source, labeled as out, in, VSS, as on the previous slide. The PFET was the drain, gate, source, out, in, VDD, and that would be the schematic representation for it. You can, there are a number of simulators out there as well that take structural representation, SPICE being one of them. Here's a representation for a NAND gate, so it's a sub-circuit NAND gate. It has port connections of VDD, VSS, A, B, and out. So it's likely going to be a NAND gate with A, B, and inputs, and out as being output, but you also have to connect up VDD and ground. So here's two N-type transistors labeled MN1, MN2, and then associate ports, and basically what they're connected to and what type of device that is. And similarly for two P-type devices and how they're connected up. So A and B are the input pins, out is the output pin, and those are net lists. And if you work through that net list, connect it up what you want it to, as it's indicated there, you would end up with a NAND gate. A transistor level representation of a NAND gate. Here's the same NAND gate, but with a little bit additional specification. This is a very old representation of a NAND gate because the technology is very large. You may not be aware of that right now, but that doesn't matter too much. Some of these parameters you might be familiar with, others may perhaps not. And it would be things like the width of the transistor. So this was an NFET, that MN1 NFET. It had a width of 8 microns and a length of 4 microns, so that's in a technology from about 25 years ago. But the point is that W and L are still important parameters. It associates an area of a drain and an area of a source, and what this allows you to do is include parasitic capacitances or capacitances of those regions. Similarly for the P-type devices, you can see the devices are wider. They have to have more drive, as we pointed out a few slides back, and as a consequence they have more drain area in this particular case and a source area. And that area contributes to the parasitic capacitances. It also has two capacitances on the inputs, which were from node A to VSS of 50 femtofarads and B to VSS of 50 femtofarads. And on the output it had 100 femtofarads. These you could have put these in based on perhaps your knowledge of the layout, or they could have been extracted from the design layout in a more automated fashion. So L and W are the length and widths of transistors, AS, AD, areas of source and drains, and additional capacitances. This, if it comes from a layout, is often called back annotated, and it's basically extracted from geometry. So a bit of computational geometry there. Structure representation, again, if it's a SPICE type net list, you may have noted that the P FETs are wider than the N FETs, and that's just because of the mobility difference between electrons and holes. In the N FET, the carrier is electron, and the P FET carrier is holes. And as a consequence, to keep the drive strength about the same, you have to make the P FET devices bigger. Bigger meaning wider. The advantage of the structural representation is a direct correspondence, basically a direct correspondence to the final implementation. The disadvantage, of course, it doesn't capture any type of functionality. In a physical representation, you're going to see something that looks like polygons. In this case, that's what they are. They're drawn polygons here, where you might have a gate region represented in red and source and drain of a transistor perhaps in green. So it's a lowest level representation of an N FET and P FET. The source and drain are diffusions, and of N-type, well, for the P-type transistor, they're P-type. And there's some schematic representation down there of the transistors. So if you're doing MEMS type work, you might need to work at this low level. In fact, you probably would have to. And you'd really be pushing polygons around in an editor that looks a lot like Photoshop. Aspects of the design sequence, well, it begins with the conceptual design and ends with testing. Of course, there's many steps between, and each company will have its own type of design flow, but there are certain things that are common to all. And to do the design in silicon, you basically need some knowledge of physics and circuits, definitely as background, some knowledge of design methodology, the conceptual design steps, and you should have some idea of circuit performance in designing cells or functional units, and simulation as well. The design sequence is typically affected by the level of design, the level of abstraction. We looked at a few of them, behavioral, structural, perhaps physical, and how the design is handed off to the manufacturer. It's very unlikely that you're doing any type of integrated circuit in-house fab, and that's basically going to be sent to a manufacturer to be manufactured for you. The design sequence itself is, or rather, part of the design sequence is design specification. That's one of the more difficult tasks to capture accurately. Early specification is usually language-based. English or any other language will do, and as a consequence, not precise or executable. An executable specification, on the other hand, is one that can be simulated, and once you have an executable specification, the functionality can be more easily assessed, and it's less ambiguous. Design library is often going to be used. It'll contain high-level functional modules or IP blocks or IP cores, accurate simulation models, and they'll be an integral part of the integrated circuit. So their IP cores, very large, ARM core example, Ethernet core, things you do not want to build yourself, but would rather use from a design library. And the standardization and use of libraries allows reuse and reduces design time. Of course, those are very desirable notions when it comes to designing anything, being able to reduce things, reuse things rather. Design sequence includes considerable feedback, and that's at every level. For example, after designing the logic circuit, simulations are performed. If the simulation shows a logic error, the designer would have to go back to his design and correct that error and do the logic simulation again. And each company will have its own detailed design flows, but many of them rely quite heavily on simulation. Here's an example of a design sequence. You have a specification, partitioning design, perhaps in hardware and what's in software, design capture, maybe coming up with a test strategy that you're going to deploy throughout the design, design simulation taking place, hardware description language, logic, circuit design, perhaps extracting things from a library as required, targeting the technology, perhaps it's going to be an FPGA, perhaps it's going to be an ASIC, in which case you have to be a little bit more aware of what the layout ramifications are going to be, as opposed to the programming implications.
Lots of simulation throughout, and all these loops kind of indicate that these are iterative. You look at detailed timing. And you're actually doing timing anytime you're doing simulation. You want to make sure that your meeting set up in hold times, for example. You can do design rule checking, make sure that it could be physically implemented. This is all done before you proceed to fabrication. And throughout, there's been a bunch of testing and test strategies done. If you happen to get to that point and the chip passes, then you probably likely move on to a next chip and build another chip within that company. If not, you're probably going to be out looking for another job because somewhere along the way, it's too costly to keep you. Here's some of the economics of integrated circuit design. Some of the salaries are up there. This again is from that same fellow's page from the previous little lecture section. And it just pointing out the digital designers, the salaries and the overheads, and CAD tools, which are relatively expensive. Analog designers perhaps getting a little bit more, an overhead, support staff, fabrication, back-end tools. So these are very expensive type of tools. These would be the ones that are related to actually producing a layout, maybe making a mask here. Again, these are very expensive processes. You're likely not going to be involved in making the mask. You may not be, depending where the design is handed off, may not be too involved in back-end tools, but in any event, they still have to be paid for. Slight little summary there: to build a chip, 2 years at $3.91 million per year, so an $8 million to design and prototype an ASIC. Pretty expensive. Here's some stats from ED Times for embedded systems. They looked at design teams, typically 13.5 members, 62% software, 43% of the designs were something new, 57% were upgrades, 12 months to complete on average. In 2011, 57 finished late or cancelled, and reuse were reported at 87%. So a brief little summary of this little bit so far. We overviewed some trends in modern IC design, some terminology, some representations, and as a designer you'll not really be concerned with the low level of details. There are exceptions to everything, of course. If you're doing MEMS type work or RF type of design, you're going to have to be pretty well versed with the low level circuit details. Anyway, at this point in time we'll take a small little break and be back shortly.